Well, hello, hello, hello. Hey, look at that. We go live and we see a satellite go whipping through the field. Isn't that cool? That's just like that. Just as I came in with my voice, a satellite went right through the field right here. Hey guys, welcome to SkyTour LiveStream. It's 10:50 p.m. on the 16th of June. And this might be the last stream before I have to go to Boulder on Friday. But we'll see. It depends how clear it is and depends what else is going on. There's so much going on. I want to say hi to Starseed, who is here first and just waiting for the stream. Thank you so much, Star, for coming along. Dagger is here. What's happening? Carol, Carl. And of course, you can see from the comments in the chat that Daryl is here. Hey, Daryl, how are you?
Hello, Mark. Hanging in there. How are you doing?
I'm okay. And here's Tim F. What's happening, Tim? Welcome, guys. And Dr. Mark in Texas. Hello there. Welcome back. Dr. Mark and I share an interesting story together, which I'm not going to tell you about because I'm just, I don't know, not mean, but, you know, it's our little story. But I actually want to let you know tonight we're just doing research tonight. Hey, Charles Smar. And tonight's a research night using the Ring Nebula. We are currently looking at the Ring Nebula, and I'm going to be imaging the ring for a while. And you saw the results from a few nights ago. Actually, I showed you the results in the stream, but I have to put them up on Facebook. I haven't done that yet, and I'll do that before I leave. We're shooting a 25-second shot now. There's the ring. Let's see how it looks. It looks pretty nice. And if you saw what we did last time, when you look at the ring like this, we actually have to rotate it to the right to make it. Okay, this is the way it looks in the sky, and I can see that it's dragged out just a little bit. So I'm going to take one more, and hope that we are looking better. But to just share with you what's going on, we're doing some research on the ring tonight. So here you can see when we look at the ring right here, okay, there is a central star right there in the middle of the ring, and that's actually, I think, like 14.5 magnitude or something like that. But this beautiful structure, this beautiful ring shape, could actually be a long barrel that's coming right toward us, and we don't really quite know. It's conjectural, but there is some research that indicates that this thing might actually be kind of a barrel. And this central part here that you see in the center here, this is sort of a blue area, and this blue area might actually be coming toward us and then going back from us, through the hole. And then this ring might actually be a little bit more of a cylinder, and I don't buy into that, to be honest with you. I don't think that's true. I think that we're actually looking at a spherical set of shells that have come off of this star. And if you look at my hands, I can do this now better this way. Okay, here's my hands. Now you're looking at the ring on the edge. Okay, this is the edge of the ring right here. Can you see through my fingers? No, you can't. What if I do this? We come around the front and the back, and now you can see through my fingers here. Okay, and see through my fingers here. So when we're looking through less material, it's somewhat transparent. Okay, and that's what we see with the ring. On the front and back side, it has a blue haze because we do have stuff over it. That's what these fingers represent. Okay, stuff that's between us and the central star. All right, and space behind. And then, but on the edge, okay, you're looking through more material along this edge. All right, and so it's going to look thicker. So the fact that it looks like a ring, in some cases, we're trying to be told that it's a function of coincidence. Yet I look at it as, I think that's too coincidental. This ring here looks to me like something that's actually been expanded as a spherical set of shells, And when you look at it from the front and the back, you're looking through the least amount of density. Along the edges, you're looking through more material as it goes along the edge. And so it'll always look like a ring from no matter what direction you look at it from. So you think about that, right? So that's my feeling. So I differ from some of the findings. I don't know whether they did studies of the motions of the gas that are coming out of this thing that might make it look like it's coming toward us. And if those motion studies are out there, and I could just be unaware of them, then that's probably why they talk about this, like that. So I don't know. But all I know is that this ring nebula right here, this beautiful little ring, right, is a gorgeous little object in the night sky. So we're going to spend some time photographing it tonight, and then I'm going to stack it and produce another set of images for you. I did that with the Eastern Veil the other night, with the Dumbbell Nebula, with part of the North American Nebula, and the Eagle Nebula, and they came out absolutely stunning. Now Daryl is here, of course, because he's going to be the comic relief.
Is that what I am?
I have no idea.
I'll comic relief or anything I can think of to chip in there.
No, you're not comic relief. You're actually a very valuable resource for all of us here. You know that. Yeah. Hey there, monkey. What's happening?
I may throw the occasional nugget out there unrelated to what you're talking about. I'm looking for one right now.
Okay. Bobby Burgess is in the house. Hello, Bobby Burgess. What's going on? Dalai is here. Yeah, this is the Ring Nebula, Dalai. It's just absolutely stunning. And we're going to just take lots of pictures of it tonight, and then we're going to stack them. But don't worry, as I take the pictures, I'll keep coming back to the image so we can actually peruse it and explore it. And depending on the quality of the sky, you'll notice, just in the previous shot, we were able to see the central star right here. Okay, but right now the central star, my hand is vanishing too. The central star seems to have disappeared, but that's a function of the seeing. And here now in this image, it's back. Let me just crank this right. Okay, come on, get you going rightward now. Here we go. There we are. Okay, so now it's better, and you can see that central star, right, which is right there. Right there. And that's, like I said, it's a fairly faint star. But it's actually bright enough for us to actually explore and enjoy and see how the Ring Nebula's shape lends itself to the name of the Ring Nebula. It looks like a ring, but it's not really a ring. I think it's a sphere, like I said, a sphere of material that you can see along the edges. It's thicker through the edges and thinner at the front and back. Okay, so it's pretty cool. Yep. So again, the Ring Nebula, we'll talk about its specifications here in a moment. Okay, the Ring Nebula is, they think, about 2,800 light years away. But see, these nebulae are very, very, very difficult to gauge distance to, and there's a reason for that. Among them, these nebula only go out to a certain diameter before those central stars, which are usually white dwarfs, those central stars cease to be able to illuminate the nebula and excite the atoms to glow like they do. And that diameter seems to be about a single light year. Now, the trouble we have is we don't know if what we're looking at, we don't really know if the star has reached that light year, if that envelope has reached the light year yet. If it hasn't, then we might, if we assume it did, then we're going to get notoriously wrong distances for it. If we assume it's already reached that light year, it could still be expanding. So getting an age of these things is very important, and that, of course, is all, again, very, very hard. We know that they're billions of years old, at least 10 billion, but maybe 8 billion, 9 billion, depending on the star. But the thing is that we don't really have the understanding really to understand how these nebulae fully operate. And there's other research too that shows that some of these may actually have something called a WR star in the middle. That's a Wolf-Rayet star. And Wolf-Rayet stars can be really, really hot and have lots and lots of radiation, more so than a typical white dwarf. And these Wolf-Rayet stars, such as are in the center, say, of Thor's helmet, which is another object that is in the winter sky that we've seen many times. Thor's helmet has the power being given to it by a Wolf-Rayet star. And it kind of looks like this bubble of gas that's expanding into space. You don't see the expansion, of course, but we do see a bubble. And these WR stars are very, very bright, very, very powerful, and they have lots and lots of radiation. Daryl, you said you were looking for something?
Yeah, but it's totally unrelated to what you're talking about.
I don't care. Let me hear it.
Okay. Well, I had been meaning to ask you and forgot. Did you see where the New Horizons spacecraft successfully made the first interstellar parallax image?
Oh, yes, of Proxima.
Yeah, Proxima Centauri.
Yeah. Very, very cool. Actually, yeah, and that kind of gave us, because New Horizons is so far out, this distance really helps us to seat officially how far the Proxima Centauri star is from us. Now, what's Proxima Centauri? Most of you know. You have Alpha Centauri, right? Well, Alpha Centauri consists of two components plus a third star that's orbiting both of those two components. The two components are capital A and capital B. That's the designation, the primary and the secondary. And then there's a tertiary. There's a third one thought to be in orbit around them, but not necessarily in orbit around them. And that third one is Proxima. And it's a little red dwarf star. It'll probably be converting hydrogen into helium in its core for potentially 30, 40 billion years, perhaps even up to 100 billion years, maybe more. Some of these red dwarfs are so small that they will continue percolating out there for over 1 trillion years. Certainly plenty of time for many varieties of life to try and come into existence out there, So that was a really cool story about this parallax of and parallax is a distance measurement. If you want to see parallax, you hold your finger out, okay, and you blink your left and right eye, and you'll notice that your finger shifts against the background of whatever's behind it. That shift angle, that shifting left and right, if you can quantify, if you can get that angle, that shift, you can get the distance. Okay, so the finger is Proxima Centauri. Your left eye and right eye is Earth and where New Horizons is now, the New Horizons spacecraft. Earth when New Horizons was here, say, and then then where the New Horizons craft is looking at Proxima, it can gauge it can measure the shift of Proxima against the stars further beyond. And that gives us the distance to Proxima to a very high degree of accuracy. And that's, in fact, many of you recall that I worked in a parallax program for a number of years and gauged distance to the nearby stars. I must have measured or photographed. Oh gosh, how many stars? I had to do probably several hundred stars, maybe more, because it was like over 3 or 4 years. So it was quite a big study, and we actually had to take the pictures. We had to get the pictures ready. We had to get the pictures down to Yale. I wouldn't do that part. And they had a Yale University had this what's called a measuring engine, which would actually study the imagery that we created and determine the precise location relative to the other stars in the images. That was really cool. All right, let's go back here and do another one of these. It was very cool. So yeah, if only we could figure out an accurate way of determining how far away these things are, because these suckers here, they're really, like I said, they're hard to determine the distance to, you know. Hey there, Chris David O'Reilly is here. How you doing? I'm looking at the images. Like I said, tonight's stream may not be that long, but we're going to be definitely looking to create some nice imagery for you of the Ring Nebula. We are incidentally using the wider narrowband filter. Okay, so this is not white light. We're looking at this with a filter designed specifically to see the colors of the blue and the red in the Ring Nebula. We wouldn't see this way in white light. So not exactly, not exactly this way anyway. So there we go. Okay, and now I'm only, because the Ring Nebula is so bright relatively, I'm only doing a 25-second exposure, and I'm only shooting it at 3200. I could probably drop that down. Hey there, Papa Tom. Carol, I said hi to you, didn't I? Oh, I should have if I didn't. I said hello to her. Yeah. So if you guys got any questions, feel free to go ahead and ask. And I'll be happy to say I have no clue and tell Daryl to answer them. I'm just kidding. We'd both try to answer them. Okay.
I'm trying to catch up with people in the stream. I'm sorry if I missed anyone. Chris David O'Reilly, hello.
That's a little weird. I'm looking at something strange in that image. I'm wondering if there was a small cloud in there or something. I mean, we do have some clouds out. We're dodging clouds tonight. You know what? I should probably do what I normally do and start up this all SkyCam. So we're going to be in continuous mode. We're going to auto save the image, and we're going to apply image processing that I determine across all of them. And now we're going to take a photo, and we're going to do a 40-second photo. Keep in mind that a 40-second photo will tend to stretch out the clouds and make them look worse than they are. Okay, Carol, I'm glad I said hello to you.
I said hello to Carol too. I don't know if she noticed or not. I said it as soon as she came in, but I had her name listed with two others.
Okay.
So Star and Daggers, I believe.
Alrighty. Well, there you go, Carol. Never say that Daryl didn't say hi to you, huh? Okay. And she would never. So let's go take a look now at... Yeah. So you gotta look... Interesting to think about the circumstances by which that occurs. You know, when we look at the Ring Nebula, what we see is the remnant of a star that's died, obviously. And there's a white dwarf in the center. That white dwarf in the center, though, gives us a phenomenal set of clues, okay? Because those clues are that most white dwarfs, if not almost all white dwarfs, are the same exact relative size and temperature. So when we see a white dwarf, we know how that white dwarf is going to react, and we know that the white dwarf is going to be a certain temperature, have certain radiations, and that's something that's really, really important. So that tells us, for instance, that when we have a white dwarf in the center of a planetary nebula, we know about how far out this kind of gas can go and still be caused to glow by the radiation of the star. That's a huge help in determining distance, to these things. Huge help.
You know, I mentioned the other night, the last stream I was on, that there is a recent APOD image, astrophoto of the day, of the Cat's Eye Nebula,
Yes.
another planetary, and they caught extremely faint nebulosity far outside what we would normally think of when we look at or think of the Cat's Eye Nebula.
Yeah.
And it made me think of what you just said, about how far out it can actually, the white dwarf can power the nebulosity, so to speak, and beyond that there might be more that we're not seeing. And I need to go back and look at it again sometime to get the details of how they managed to do it. But they grabbed, here's this beautiful APOD picture, and what we think of as the Cat's Eye is this tiny little thing down in the very center with this huge amount of stuff going on around the outsides.
Yeah, and that's something that is actually here too. Okay, when we look at the Ring Nebula, we don't see all the stuff that's out here. There is so much more all the way out here, around this Ring Nebula. I mean, stuff all the way out in concentric rings around the ring that come out, which is why I keep saying that I believe this is a spherical shell of expanding material, not a barrel like they suggest. That we're looking down the length of a barrel into this thing. I don't think that's true at all. And the concentric rings are part and parcel to what happens when stars get old. They begin to slough off their outer layers, and they will alternately puff up and then come down, puff up and go down, And that puffing up issue, that puffing up problem, is something of a giveaway to what's really going on inside the star. And that's something that I think we want to pay attention to. I'm going to just try a little something here. Does that work better? Oh, yes. Yeah, that's much better when I use bright light. How about the Arctic Aurora? What is that? Oh, that's going to be bad. Oh, maybe not. Yeah, it's okay. Anyway, I'm trying to just work out the best light for... Oh, gosh, that's terrible. Supernova. But we'll just do this. Try this for now, because for whatever reason I can't, the light isn't working fully with the process I was doing, so we'll forget about that for now. Let's just the idea is to get you the information. But look, we have this now. Okay. Where's it going? What are you doing over here? Get back up there. That's better. Just always trying to horn in on my action here. This nebula, when the stars age like this, for a star like this, could be a little bit larger than the sun, but not much, or about the size of the sun. And so, as they age, what happens is they're fusing hydrogen into helium in their cores. Okay, and that hydrogen is fused into helium. The core temperature reaches 13 million Kelvin, and that is the temperature at which hydrogen can fuse into helium. It starts that spontaneous reaction where hydrogens can be crunched together because of the overlying weight of the pressure over them from the star. And they make deuterium. Then they make an isotope of helium, and that gets further refined into another isotope of helium, and it liberates another hydrogen out of all that. And that's called the proton-proton, and I call it reaction. It's not really a chain. But that proton-proton thing is how smaller stars like the sun actually, create this reaction to make helium isotope from hydrogen. And the stars only have two known methods, two methods, but only one is in use at any time in these stars. And one of them is this proton-proton thing where the hydrogens are crushed together. Another one is the CNO cycle, and that's a carbon-nitrogen-oxygen catalytic cycle. Each of those atoms catalyze and help make hydrogen into helium eventually. And this happens in more massive stars. So when we see this reaction, it tells us something about the chemistry of the star, the mass of the star. So if we see the CNO cycle in action, we know the star has to be a certain mass. It has to be much more massive than the sun. And so that's what we see. So we don't, with stars like the sun, when they run out of hydrogen fuel, they begin to shrink. Okay, because the outward pressure of the radiation has been reduced, because the hydrogen fusion reaction pushing out is overwhelmed by the gravity of the star trying to collapse itself. So it begins to get smaller again. And as it does so, a lot of the hydrogen out here in the star, which is not fusing, by the way, the entire star is a hot plasma except for the core. In the core, it's even hotter, and that's where fusion occurs. Everywhere else, it's plasma, which is not fusion, okay? It's just atoms that are stripped of their electrons, and it's protons and electrons freely moving separate from each other, okay? So that plasma in the outer parts of the star is now moving toward the core. As it gets near the core, well, guess what? Now the core is getting enriched with more hydrogen as the star gets smaller and contracts, because the outward pressure is reduced because it's used up a lot of the inner hydrogen in the core. So it collapses a little bit. And then some of that hydrogen is now in the core. Uh-oh, guess what? It's hot enough to fuse. Fusion starts again, and the star begins to expand again. That happens several times. As you can see, every time it does that, okay, I don't know how that song got in there. Every time the star begins to collapse and then go like this and slough out again, or puff out again, on its way back in, or on its way out, a layer gets liberated from the star as these stars get older, because the star becomes so big that those outer layers are kind of in a netherworld where they're kind of attached to the star, but the outward pressure that's just enough to, at that far distance, is just enough to push them away, and now they're free of the star. They become free, and so they go outward, and the star then collapses, and the layers that are still gravitationally bound collapse, but the outer layers keep going outward. They got liberated, and that just happens. Poof, poof, poof. And you see these successive rings. See, successive rings. See, a ring.
Okay, I found this on the web for a series of successive rings.
Oh, that's so
Check
funny.
it out.
Did I say hello Siri? I didn't say hey Siri, did I? But that's funny. Anyway, so you see these rings here. These rings are formed by these successive puffing out of the star here. So poof, 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 and they got released. All right, and stars also have complexities that make that whole action a lot more difficult to explain. There are nebulae called bipolar nebulae, and that means that they have more stuff at one side and the other, and less in the middle. You see, this is sort of a nice circular ring. There's a shape here that's circular, but we don't see that in some nebula. Some nebula don't have this beautiful shape. Some nebula actually have an hourglass shape, and that's one like the Dumbbell Nebula that we know. And maybe we'll take some shots of that too. So the Dumbbell is one of those nebulae that's known as a bipolar nebula. This one, on the other hand, is not. This little guy is just a beautiful little ring that we can explore from the point of view of it being a fairly standard planetary nebula. So as the star gets older and it starts doing that puffing, it runs out of the fuel that it's using, and then it starts to shrink again, and it can only bring more hydrogen into the core so often before it has to bring other things into the core, and it'll start bringing helium into the core. And then if the temperature reaches 100 million Kelvin, then the helium can be fused into carbon and other products too, and other isotopes. So the helium, it's called the helium flash when that occurs, that could cause the star to blow way up because there's lots of helium in the core at this point. So there's going to be lots and lots of helium that can be used now to do that, and the star will blow way up. All right, now those layers that are attached to the star are even further moved away from the center of where the star was, and they end up going even farther away from the star. All right, and then as the star runs out of the helium, it begins to contract again, and finally what will end up happening over many millions of years is the star will then start to shrink down, and no fusion is occurring anymore, so the star continues to shrink. There's still an outward pressure of some radiative energy, all right, and much of that is in the heat realm and in the ultraviolet realm, because as the star pushes off its outer layers like that, it's further and further and further exposing the core, and that core ends up being exposed. And when we look in the center of these guys and we see that white dwarf, you're looking actually at the core of the star right there. That's the core, what's left. All right, it's about the size of the Earth, incidentally, and at a distance of 2,000 plus light years, you can still see it pretty bright. That's a really bright object, guys. That's a really bright object to be able to be seen from that far. So that's what we're talking about here. Is a amazing nebula that's the result of star death, but in a way that is absolutely amazing and impressive. The universe generates such amazing beauty, but it does so and provides something in return. It provides the building blocks of life. Now, when those stars get so big and bloated, they get way, way big. Those red giants get so big. Out here, the star core is way in the middle, remember. Out here, what will happen is this outer layer, it can be so cool, so low temperature, that you can actually get molecules forming out there. Molecules forming in the outer atmosphere. Diatomic hydrogen, H2, for instance, can form out there. You also get, in some stars, you get a dredging up from the middle of the star, from the central areas within the star, not the core per se, but around the core, of carbon atoms. And when you get this extra bunch of carbon atoms near the surface, it actually produces almost like a dark soot, carbon soot, all right? And that carbon soot will make the star look, can you guess what color?
Red.
You got it, Daryl. And that red is the result of something called a carbon star. And they are probably the most beautiful stars in the entire universe. But they represent the state of a star that is in its death throes. So as beautiful as it is, it's heralding the end of a star. And so it's something that I would have to say is pretty kind of a scary thought to me, but I think that it's something that would be really neat to be able to see up close, wouldn't you? I'd go.
Really close, respectful distance, perhaps.
Respectful distance, yes, of course. Of course. So, I mean, that that's like seeing a volcano erupt. I'd like to be at a respectful distance. Thank you very much. Yeah, I don't want to be staring down into the cauldron of imminent doom. Yeah, you're right. But hey, I mean, we have a reasonable night considering the quality of the sky. Speaking of the quality of the sky, let's go see what we got. Oops, we had the light on. The lights are on outside because one of my sons came home, and I can't really tell what we got right now. Those are not clouds. That's condensation inside the dome of the camera there. Okay, no worries. When I go out inevitably to have to move the dome and run away from bears, I will certainly wipe that off as I'm running away. Hello, Kathleen Solway Kessel. How are you? Nice to see you here. So when we look at this, keep in mind that we're seeing the chemistry of the star exposed to us now. Because when the star's outer layers are sloughed off like that in that pulsation phase I was telling you about, then these layers, the outer layers, will be, they'll generally be some hydrogen, maybe some of the neon that was in the atmosphere of the star. The inner layers are going to primarily be, there's many different layers in here, many different chemical signatures, but the predominant color you see is the one that actually is the one that dominates. And this particular case, it's oxygen 3, which is doubly ionized oxygen. And what does ionized mean? Ionized just means that in an atom you have a proton and an electron in a hydrogen atom, okay? If I ionize that hydrogen atom, the electron is knocked off the atom, not because something hits it, but because it absorbs energy. And think of it as it raises way up into a much, much higher energy level, to an energy level that is so high that it's no longer constrained to the atom. That's ionization. And another hydrogen atom nearby could steal it if it was without its electron. So whenever you see ionized hydrogen, you can be sure that there's some atomic hydrogen that has got its electrons, and there's some that is going to be just ionized with just a proton floating around, and a number of electrons also just floating around as well. So there's an awful lot to the chemical understanding of what's going on here. This looks like a simple ring nebula. We can certainly enjoy it for its color and its beauty, and what it means, the white dwarf in the middle. But we can also look at it from the point of view of saying, wow, this is really kind of a fundamental crux of understanding what happens in the universe to the stars, So I'm pretty sure that we'll see more of the ring nebula, if we haven't actually seen too much of it already tonight. So anyway, and to think of it, I was just going to be doing a research night and just letting you come along for the ride. But I decided that I was going to stream it too. If you like when I stream the research nights, let me know. And I'll be happy to continue that when I do that. For those of you that want to see more objects over the course of a night, well, then maybe research nights aren't for you. But you get a lot more information about the objects when we do the research nights, as you can see, because we've talked about the chemical components, we talked about the white dwarfs, and I got to add a couple of things about the white dwarf to help you understand why not a neutron star or a black hole. Why a white dwarf, and what's the difference? Well, white dwarfs occur with stars that are less than 1.44 solar masses. Now,
Chandrasekhar limit.
That's right, Chandrasekhar limit. That's the limit that the famous astronomer and astrophysicist Chandrasekhar, that's his last name, it's Subrahmanyam Chandrasekhar. He discovered this because of when he was doing research, and he found that stars that are less than 1.44 solar masses will always create a white dwarf unless something crazy happens. And what is a white dwarf? Well, it is definitely an odd star. If it's still considered a star at all, it's actually the death husk of a star that's less than 1.44 solar masses. And its surface is kind of like a hard shell. Not a really hard shell, but a somewhat hard shell. Yet we know a star as being a plasma that you can sink into. If you could go through a star and get through the core, you could come out the other side, because the star is, you certainly can't do that in reality, but the star is actually a gaseous object. It's not a solid object. So what's with these white dwarfs? Well, the white dwarfs are compact, and so as the star collapses, its gravity, once it doesn't have any fusion to do to radiate pressure outward, gravity crushes the star and crushes the core. It crushes it so much, in fact, that the atoms that are near that part of the star in the outer core, the inner core, are compressed so much that the electrons and the protons are all squeezed out of each other, effectively. So if you think of it as a checkerboard where you have red and black squares, imagine that an electron is in each and every square, but only one electron. And only one electron can be in one of those squares. That's the conditional state that's happening in a white dwarf. And because of that, it means that once those are filled, once you have a checkerboard full of electrons, you can't crush it anymore. All right? And the pressure that the electrons push back with is the pressure that holds up the white dwarf from collapsing further. And that's called electron degeneracy pressure. Don't worry about the name. Just understand the checkerboard thing. Okay? You fill the checkerboard with electrons. Okay? And they each can't they can't push against each other any more than they do, and they can't actually do anything, all right, but push out. And you can't crush them anymore. Now, that's with 1.44 solar masses and less. At greater than 1.44 solar masses, something else happens. And that something else that happens is you go right past the electron crushing in the checkerboard, and now the checkerboard is filled with neutrons. Okay? Now, neutrons are made of three little things, and those are called quarks. Now, a proton is actually similar in some ways. It's also made of three quarks, and that's Quarks. And we'll talk about this in a second. Don't worry about it. A quark, to make a proton, you basically have two up quarks and one down quark. Okay? I know this sounds like gibberish, but two up quarks are 2/3 of a charge each, and one down quark is minus a third. Okay? And that adds up to a positive 1 charge. Now, the neutrons have 2 down and 1 up. So 2/3, minus 1/3, minus 1/3, and 2/3. 0 charge. And that's what a neutron is. So there are conditions, okay, in a star where you can actually create protons from neutrons. And that means you take one of those quarks that's down and flip it up. And now that's a proton. That process occurs in stars like the Sun, and it takes a long time. And it's called the S process, or slow process. It creates the higher elements in the periodic table that are in that we'll find in the star's atmosphere when the star doesn't ever get hot enough to actually create them through fusion. But it creates them through this, it's called beta decay. It creates them through this decay process. And that's the S process that we're talking about. It's really phenomenal because that is where a lot of the elements from the periodic table come from. You know? And that's why they're spread far and wide throughout the universe. It's really, really something. Now, when you have a star that's greater than 1.44 solar masses, one of the problems we have is that when the star does collapse, right, it can collapse to the point where the neutrons themselves are filling those checkerboard squares. Okay? And the neutrons have a pressure all their own that won't allow them to be compressed any further. And that is called neutron degeneracy pressure. Sometimes you're in another world where the stars won't just contract to be a neutron star, but the stars will go supernova and explode. And the pressure at that point can go right past white dwarf stage because the star went supernova, was already massive enough beyond 1.44 solar masses. And you're going to get a supernova. And the pressure on the core will turn that core basically into a neutron star. And now that neutron star will simply be out there forever and ever until it begins to cool as it will. Now, the surface of a neutron star is as hard as a billiard ball. I mean, it really is. It's like a shell. And sometimes neutron star shells can crack like an egg. And when they crack like an egg, then they can release a tremendous amount of energy. We saw that two neutron stars merged and collided, and this created a huge event in astronomy. Two black holes collided. Now, what's a black hole versus a neutron star? Well, now if you get to about 2 to 2.4 or 2.2 times the mass of our sun, between 1.44 and 2.2 times the mass of our sun, you might get a neutron star. But if you have a supernova and it's the core is greater in mass than about like 2.5 times the mass of our sun, that might actually collapse and form this odd thing called the black hole. Now you might want to talk about, well, is this the neutron degeneracy pressure? No. Is this electron degeneracy pressure? No. It's something that we can't readily accept or explain, because we have to deal with a term called in an object called a singularity. It's like imagining that all of the material in a star is compressed down to a single tiny point. That's certainly the way it acts. All right, but a black hole is a phenomenon that it has such high gravity, it actually warps space itself. Now, what does that mean? Warping space itself means that it actually takes the fabric of space. If this napkin was space, a black hole could twist it and warp it. And so if a black hole was down here below me, it would warp space like this, And that's something that is really hard to understand, because then you have to say, well, wait, what is space? And is space have mass? How is a black hole warping it? Well, obviously gravity affects mass, but gravity also affects space. The existence of the black hole creates a warp in the fabric of the very space itself. And again, you say fabric. What fabric? Is there linen out there? I mean, cotton? What's going on? The fabric of space is a mathematical construct. Our observations fit what we see. Now, we have heard the term that light never can escape a black hole. Yet we know that light, photons, that is, the energy packets of light, these energy packets have no mass. But I just said that gravity affects mass, didn't I? Why, yes, you did. Well, what, are you, an idiot? No. Sometimes. But no. What happens is the mass that we see that's affected is affected by gravitational fields, and photons do not get affected by gravity. So therefore, why can gravity be so strong that not even the gravity of a black hole be so strong that not even light can escape it? Why is that? And the answer is stranger than fiction. The answer is that okay, we gotta fix that. I'm wondering do I have clouds or something, or maybe I just don't have the settings right. The answer is that when we look at the fabric of space being warped by a black hole, the black hole can warp it so much that light, which has to follow the constraints of space, light follows space. So if the black hole warps space, light just follows it. And if the black hole warps space to be kind of in a circular shape, once it gets beyond that magic spot called the event horizon in a black hole, why then the light will spin around forever and go around inside the black hole and never ever come out. And that is something that gives us the reason why light can never escape a black hole. Light's not affected by gravity, but but light has to follow space in the same way that a car has to follow the contours of a hill. Okay, if the hill was actually space and the car was the photon, well, the car has to follow the contours of the hill, the photon has to follow the curve of space. And that's what we see with a black hole. That's why light can't escape from a black hole, because space itself is warped. It's a two-stage problem. It's not just the gravity, so strong that light can't escape. It's gravity is affecting space, and light has to follow space. So therefore, light can't escape if it goes in too close to the black hole and enters the black hole through that magic place known as the event horizon. And the size of a black hole depends on how much mass it has. There are what are called supermassive black holes, which some of you know in the chat. Supermassive black holes are in the center of galaxies. We have one in ours. The Andromeda Galaxy has one. And the Virgo Galaxy has one, M87. Now that galaxy is 55 million light years away, and using a special telescope called the Event Horizon Telescope, a couple years ago, astronomers were actually able to image, for the first time in human history, an actual black hole. And what they thought, according to Einstein's equations, that the shape of the black hole would be and how it would look on an actual photo of a black hole was exactly what they predicted, and it was exactly right. This is where science works. Okay? This is a case where science works. A case where it doesn't work has to do with the expansion rate of the universe, which we've talked about, and which I'll talk about with George Norrie on Saturday. Okay, so that's a case where we just don't have a real idea what's really truly going on, in my view. I don't think we really understand it. So tonight we've talked about, we've talked about these white dwarfs. We talked about these guys right here. We talked about the pressure that they use to actually hold themselves up, and thus their radiation they expend and they put out actually causes the nebula out to a certain distance to glow. And so they're really beautiful, and they really are just an amazing universal find. The Dumbbell Nebula is another one. M76 up in the northern hemisphere here is actually another one, and there's thousands of these dying and dead stars. There's one in a very famous cluster in the constellation of Puppis the Poop Deck, as Daryl and I have talked about. M46, I believe, Daryl?
Yes, M46.
Yeah, M46, and in the middle of that cluster you'll see a little ring of blue, and that little ring of blue actually has a tinge of red around it. Looks very much like the Ring Nebula, but at a tiny scale. Really interesting. So this is one of those cases where we see that the Ring Nebula seems to be replicated elsewhere. Now there's another Ring Nebula in the sky, and it's called the Little Ring Nebula. And I'm wondering if we can find that tonight. I don't think so. I'm not sure. But in any case, I want to just say hi to Amanda Shaw. Hello, Amanda. And David Schmidt. Thanks for coming in. I see you there. You've come in to say hello and hang with us. We're having a great talk. We're talking about electron degeneracy pressure. Kind of like peer pressure, but from an electron, if you will. And that's sort of neat. And so we'll take another shot of this.
Talking of nothing in particular, you talked about Quarks earlier. Are you familiar with an English rock band from back in the day called Hawkwind?
I am not. Do tell.
You never heard of Hawkwind, really? They did a really good album called Quarks, Strangeness, and Charm a long time ago.
Quarks, Strangeness, and Charm.
They're a sort of English science fiction rock group back in the day. Michael Moorcock, an English sci-fi author, worked with them some, I think. And of all people, Lemmy Kilmister from what's his face, Ace of Spades. He was in Hawkwind a long time ago.
Wow.
It's an excellent album. If you ever get the chance, you got to listen to it. Quarks, Strangeness, and Charm.
Well, and now with Daryl saying that, I'm afraid that we have to explain what strange and charm is.
Well, it's all my fault.
Well, go ahead. You want to explain it, or do you want me?
No, you better, because I don't remember.
Okay.
Makes a neat album title.
Yeah, it does, actually. There's different types.
Well, there's properties. There are properties of quarks, but you're going to have to say it.
Yeah, there's different types of quarks. Yeah, and they have different characteristics. They have up and down quarks. There's beauty. There's strange. There's charm, and a number of other characteristics. And I know it sounds sort of silly, but they actually have a special meaning. That some of them are subject to certain forces, some of them are not, and so there's a different way to talk about quarks. Let me get you the list of all of them if I can. We have top, we have up and down, we have charm, and Okay, what's this one? That's not helping me. I'm trying to just get the, I'm just trying to get the value, but it's not coming in. Because I don't remember every detail of different types of quarks. But I'm trying to figure out, like, which ones react to which. But Daryl will find it, I'm sure, if he's going to hunt it down, because I'm doing 5 things at once here.
I'm sorry, what did you want me to look for?
Oh, if you want to look up the different types of quarks, we can talk about it.
Oh.
And you can do that in the background if you want. I did want to mention this, though. For those that heard the story about planets forming in the Pleiades, okay, Science Daily put it out. Astrophysical Journal had a story. Not that you all read the Astrophysical Journal. You're not all nerds like me. But the story is that there were planets forming in the Pleiades cluster. Now, it's very important to understand what the Pleiades cluster means and versus the Pleiades. They can be used interchangeably, but they don't mean the same thing. Okay, in the end. The Pleiades cluster is a cluster that's far greater than the 7 sisters, and it consists of, like what was it, 80 to 100 stars that are all in the same general region. And they aren't hot B stars. They're not all hot B stars like the Pleiades we know. Those Pleiades that we see in the sky, Maya, Taygeta, Alcyone, Pleione, etc., those stars, Atlas, those stars are all very, very young B stars. But part of the Pleiades cluster is other stars too, like F8 stars, which are almost G-type stars. In other words, close to our sun in type. And they're lost in the muddle because the big, bright, beautiful blue stars. But it looks like there is some disks of debris around some of those stars. Now, because there's so much material there, and it's because the Pleiades cluster is traveling through dust, we see lots and lots of debris wherever we look over there. Which is why when we take pictures of the Pleiades, we'll see these beautiful curtains of dust around them, you know, of the stars. But the truth is, it seems to indicate that there's planets forming in the Pleiades, but we don't have any direct evidence of planets themselves. Only that maybe there was a collision of some pre-planet, protoplanet type material that left behind tons of debris. I dare say the sky's getting better. You know? So, that said, let me come in here and see if I can do some processing to get us back our stars. Yeah, there's plenty of stars. The trouble is that I have a little bit of layer of what looks like ice. See, the dome looks kind of fuzzy. There's a layer of ice. You can see some clouds down here. Those will be heading our way. There's a little cloudiness over there. But for the time being, we're in good shape, right? So let's keep going, shouldn't we?
Sure.
Yeah.
Mark, will you excuse me for just a moment, please?
Well, sure I will. Go for it. So anyway, that's the story on all this, on the stars in the center, okay, of these planetary nebulae, and of the nature of the white dwarf right there in the middle. These guys are really hot, like I said, and they give off a lot of radiation too that causes the stars in the middle or causes the gas in this whole nebula to glow. As I said, it goes out to a certain range, and then that distance, beyond that certain distance, it can't do that anymore, which is kind of cool. helpful for us. You know. Okay, I'm just adjusting something here. Yeah. So anyway, I think that's pretty interesting. Hopefully you think it's pretty interesting too. And I'm kind of close to that. That's a little unnerving. I shouldn't be so close to that. Yeah, it's it's hot. It's got a lot of ionizing radiation. So yeah, I'm silly. What can I tell you? But I'm enjoying your company. And as I said before, tonight we're doing it's a bit of a research night. And there, our research night is basically, I'm doing the Ring Nebula tonight. Just doing a bunch of shots. I'm going to stack them, process it, and look for any other faint detail that I can see. You know? That was funny, Katie. I might get sucked in. Nah. If anything, I might get blown away, because that's a lot of radiation that's blowing away from that central star. A lot of radiation. So it's a very, very powerful. That little tiny star in there is about the size of the Earth. Yet it's over 2,000 light years away and still quite visible. Hello, Daryl. Welcome back.
Oh, thank you.
Yeah. Oh, what'd you ask earlier, David? Let me read this. Oh, is it spinning? You mean the white dwarf? I assume you mean the white dwarf. Yeah, I'm sure the white dwarf is spinning. I do not know its spin rate, though.
Everything is spinning.
Yeah, nothing is still in the universe. There's nothing that's not moving. Right down to your tabletop. Obviously, your atoms in the tabletop are just going to town. They're having a field day. But because they're all... Because of their structure and the way they bond, the way the atoms bond into molecules, we have objects that are hard, you know? Okay. What the heck's that, Daryl?
I'm sorry?
What was that?
What was what?
Did I hear just...
That was an airplane going over.
Oh, okay.
C-130, I believe.
Yeah, it sounded like... I was going to say, it sounded like a C-130 to me.
Yep.
And those of you know I'm going to Boulder, Colorado Friday. Daryl lives in Colorado, but we're not going to be able to get together at all because I'm there for, 24 hours. I arrive Friday. Saturday, I shoot at Gaia TV. I'm going to do the show Deep Space in the morning. And then I'm going to do the show Beyond Belief with George Norrie in the afternoon. Then I go back to the hotel. And the following morning, I head to Phoenix, Arizona. And I was supposed to go to Phoenix, Arizona to build the observatory for SkyTour LiveStream West. But with COVID, we're actually putting that off until July 13th. And, it is what it is. I will not endanger people by bringing a building crew out to the desert, to the land and property of my very, very dear and close friends. I will not put their health at risk when they're being so gracious to me. So it was a no-brainer. I didn't even have to think about it. I've waited this long to actually build this observatory. I can wait another month. Now, can you wait another month? That's the question. I'm sure you can. So I will be doing this to make sure that it gets built right. But here's the thing. next month, again, assuming that everything is fine, I think it will be, we're not only going to build the building, we're also going to build the rails that come off the building. They will take the roof, which slides off the building and goes in the concrete. We're going to do that too. And I may also be shipping this very telescope that we're using tonight out there to be there when I get there. And we might actually be imaging from this telescope with a live first light view from SkyTour West in July. Now, it depends how long I stay. I think my initial trip here was going to be like 9 days. Now I'm going to get to Phoenix and 2 days later come back here to Connecticut. But the ticket has been changed to go back out there. I have a ticket now for July 13th, and then I'm going to go off. And this time it's going to be maybe 10 or more days, maybe 12 to 15 days. And I'm going to get this thing running because I said I was going to have this up and running by the end of July. And I mean it. I want first light by the end of July. I've got to do everything safely, of course. I've never worn a mask in the desert when it's 115 out, but it's July in the Sonoran Desert. It's not going to be cold. Even at night, the temperature only gets down to about 80. Depending on the temperatures, though, you can have a chilly wind come through, and after being subjected to temperatures of 110 all day long, an 80-degree breeze is going to feel like it's a 30-degree breeze to you. Trust me, I know. And Tara knows too. She lives there. And Tara, I thought, was in the chat earlier. So if she's still here, Tara, pipe up and can tell them that I'm correct, right? Yeah. And we're actually talking about other things to do to the building, once we get out there. Tara's actually an excellent artist, and she might actually be willing to paint a mural on the sides of the SkyTour LiveStream West building. Now, I didn't put that bug in her ear. She offered it, and I thought that was just a splendorous idea. So won't that be cool? Yeah, I think first light, we're probably going to have a big crowd on hand for that one. Probably not as big as the lunar eclipse, Daryl. I mean, we did the lunar eclipse and caught the meteor hitting the moon. Mm-hmm. At that peak, we had almost 5,000 people watching at the same time.
I remember that.
Yeah. You were there, right?
I was.
Yes, sir. Yeah.
And purely through serendipity, you caught the meteor hitting the moon that night.
Yeah, that's right. Yeah, that's right. Okay.
Serendipity. That's one of my favorite words.
Yeah, and serendipity, for those that don't know, is a chance discovery, or by chance. Okay, a serendipitous discovery is a purely accidental, by chance discovery. Well, you'd be really surprised to see how much science is actually serendipity, and that's it. Serendipitous science. Really interesting.
I always like to think of it as a happy accident.
Exactly so. Hey, that's what my mother says I was.
Huh. Well, I was a surprise. I don't know about serendipitous. They were only expecting one of us, and
they got
after my brother came out, I came out 9 minutes later. This was back in the days before, ultrasound and all that happy stuff nowadays.
Wow.
Or even knowing what the kid's sex was going to be before birth.
Wow. Yeah. Yeah, Tara says it'd be fun to do something like, something to the building facade, she thinks. Yeah. You should see this woman's artwork. Tara is an absolutely phenomenal artist. I was really surprised. And guess what else? she does art with chainsaws as well. Not just
Cool.
paints and delicate paintings. No, chainsaws. Now, is that someone you want to ever get mad at you? No. Does art with chainsaws. Can you imagine? Wow. I've seen people do that at fairs, and usually these big burly guys wielding their still saw. Next thing you know, oh, it's a bear, or it's an eagle. Well, Tara is not like this, one of these well-built guys. For instance, she doesn't look like she can hold a chainsaw. Sorry, Tara, I'm not trying to pass any judgment. But boy, oh boy, living in Arizona, hiking all the time, let me tell you, I bet you that's part of it. Staying fit, And I feel good about that too, I plan on continuing to do my hiking. I really would like to get back to the martial arts. I haven't been doing my martial arts for a number of years now, and that's really bothering me. I have my stretch. I can still stretch. I can put my foot way up here if I want to when I first get up, because I maintain my stretch. But what good is your foot going way up here? That's usually what precedes falling down. But it's still, I try to maintain. And my sons are helping me do strengthening exercises as well. Romanian deadlifts, and I'm going to be doing some negative pull-ups to try and get the upper body strength back. I never really had it after the 5 years ago after the surgery. It was really like being hit by a train, especially because you have to get your core working again. Your ankles, most importantly, because you don't want to roll your ankle, learning how to walk again. And these are beautiful. These are looking good. And I didn't. The thing was, I didn't fall once during my recovery, and that's not meant to be like a brag or anything. It's just I focused on my ankles, and I would try to stand up on my balls of my foot, and it was impossible. I just couldn't lift myself, so I pushed myself up with my arms when I got my arm strength a little bit back, and I pushed up, and then I let myself fall down slowly, and so that's called a negative. And so that was a negative, ball foot move there, and so that way I was able to get all that strength back. And I'm going to do the same thing for the chin-ups and stuff like that. I mean, it doesn't hurt that I dropped 17 pounds this month, so that's by drinking water all day long, folks. Just drink water, and then have one meal a day. I ate dinner, and that's it. During the day, nothing. I just drink water, and you know what? I never thought I could do it.
We talked about this recently. Some call it intermittent fasting, and
yeah, that's right.
It's supposed to do all sorts of good things for you. Some say it helps wake up your stem cells to go out and
wake up, guys. Wake up.
Repair your body.
Yeah, wake up.
Regeneration, I guess you'd say.
Yeah. And the nice thing is, if you do one meal a day that's smart, then you don't end up spending so much time trying to fight off all these nasty chemicals you're imbibing, and I don't want to do that anymore. I should I don't need to, but I mean, I can tell what the sky looks like just by looking at the ring. This looks pretty good. So there's a ring sitting all alone out there in the sky, and you can't even see it with your eye unless you have a telescope. Yeah, keto diet is good too, Dalai. But so what I'm doing isn't a diet. I'm just changed my eating habits. I'm no longer eating during the day. I only eat at night, And some people say, oh, you should eat at lunch, and not at night. Well, see, if I eat at night, then I eat less, and I'm still full. Like tonight, I had one helping of absolutely wonderful dinner that I could have easily had 3 helpings of, and I didn't want any more. And people say, well, you shrunk your stomach. Well, I don't know that it actually shrinks. I think your body just gets used to less. The hardest part was the first 2 days. The first 2 days was the hardest part. And then, boom, it worked. And for those of you that know who this person is, because this is the person that I absolutely thought was, crazy for doing this approach, and that was Ket Torv Olsen. She's the woman I toured Norway with last August, and she was doing this water diet, and I thought, what are you, crazy? That's the stupidest thing I've ever heard. And then she made me watch a documentary on it. Yes, made me watch, because I had to stay with, spend time with her and stay with her, so I had to figure out what to do with my time. She said, watch this video. So I watched this video, and I thought, well, okay, that's kind of interesting, I guess. And next thing you know, I didn't think it was as nutty, but I still thought it was nutty. So I get home here, 6-8 months goes by, and I look down the scale, 198. Oh, man. 198? I feel sluggish, I feel fat, and I don't wear it like, in my stomach. I wear it everywhere, right? So I said, I'll try this water thing, but I'm not going to do it like constant. I'm not going to do like a 15 days of only water. That's nutty. I can't do that. So I ended up, that's pretty. I ended up doing, water all day and then eating at night. And I watched the pounds melt away. I watched my blood pressure come down. I watched all these good things happen. I watched my body cleansing itself, and I watched myself gaining energy that I didn't think I had. If you think I didn't have energy, okay, I don't drink caffeine anymore, and I just went through this long tirade about white dwarfs and these things, right? And we talked about white dwarfs and neutron stars, neutron degeneracy pressure, electron degeneracy pressure, all these things. That's coming from the energy I have because I have this new body clock that works so well with this approach. And I have no need. I've been tempted by people with candy and food. Like my niece brought me Dunkin' Munchkins. Okay, basically the hole. They figured out what to make the hole into. Hey, let's make a donut out of the hole. And the chocolate ones that were iced and the jelly-filled ones. Really good. I know that. I remember how they tasted. Okay, and I looked in the box, and I could smell them. And usually that's sort of like the death sentence for you. If you smell them, you're going to eat them, right? And I actually wasn't interested. I said, well, at dinner time, maybe I'll have a couple. And I did at dinner time. But I didn't feel the need during the day, and that served as my sugar fix for the day. It's crazy. And I've encountered other people that have basically gone on this type of approach, and it's like, I thought they were nuts, but here I am doing it. And I'm living proof that it works. I mean, you probably don't remember me at 198, but you see me at 181 now. I think that's kind of speaks for itself, Yeah, no caffeine, David. I actually don't drink coffee. I don't like coffee, and I will though, and I will not lie. And this will mean something to you, David, because you're teaching in the Bangkok area. I used to really enjoy, and I'd make my own and buy it in bulk, Thai iced tea. Thai, Thai iced tea. I absolutely love that. It's a green tea, but it's tinted orange, okay? But the Thai iced tea flavor, you use half and half. and you pour that in like milk into coffee, right? Really high in caffeine, and I could drink 1 cup of that and be good for the day. You know, it's amazing. It lasts so long. It's really, really good. You know, really, really good. So let's see here. I think I've probably taken maybe 45 or 50 shots now of the Ring Nebula. Do you think that's enough for me to do a good stack there, Daryl?
I'm sure it's a good start.
Good start. Yes. See, don't you love this guy?
I don't know. You know, I haven't kept up with digital imaging. I know people stack images. I don't know what a typical good stack is. I've seen some where, God, they'll shoot hours and hours of exposure, and they'll sit there and stack them all together, doing 30 seconds or 5 minutes at a time for many hours. You're talking a lot of images to stack.
Yeah, that's true. By the way, Anahata77, thank you. That's very nice compliment. Thank you very much. So yes, I find that when I stack images, I stack minimally 12 images, but I have stacked 30, 40 images before, and it's not bad. It's not a bad thing to do that, but you do reach a point of diminishing returns, and it somewhat depends on the object. It depends on the camera, the sensor, etc. But if you're going to stack, say, if you're going to take 40 images, then technically I should go and take 100 dark frames. When you stack images, they all stack on top of each other, and the noise is averaged out, but the dark frames allow you to actually get rid of more of the noise and produces a better view of the object in question. A dark frame is just, imagine putting a cover on the telescope and taking a picture of the black. Okay, and then you have other frames where you take the shortest exposure possible with the camera, and it just goes on and on. There's ways to improve this even more. What are you saying, Daryl? You used to be so pretty?
Yeah, once upon a time.
I don't get it either, guys.
I'm sorry, you're talking about the intermittent fasting, the water diet. Okay. Kind of started all this in the chat room.
Okay. That's what I get for just sort of peeking in and not paying attention. All right, you know what? Let's do this. This exposure, when this is done in 30 seconds, I want to go check out something else. And I said I was only going to do the Ring Nebula, but I think you know by now that I am, Mark, just one more D'Antonio.
You mean Mark doesn't know when to quit, D'Antonio?
Fair enough. And the first thing I'm going to do, because I always love to do this, is I absolutely adore my favorite little star here. I just adore this star, and I want to go check it out. Actually, seeing Albireo, which is the head of the swan right there, the eye of the swan. Seeing Albireo is a wonderful, wonderful way to explore the night sky and check out if it's really nice and clear. Because when I take a photo of it, you'll see whether it's really nice and clear. And in that photo will show us that, look at that look at that guy. This thing it's got a blue star right there. It's a B8 star, okay? And then that's a K2 K2 Roman numeral 2. So that's a giant K star, and this is a beautiful blue star. And so this blue and orange really just looks stunning. really does. So what I'm going to do is I'm going to bring that a little higher in our view, and then we will head over and image a few other things. Okay, there we go. Hey there, Marco. How are you? Okay, so let's go here. And now let's, okay, and if we look at our telescope, we can actually see in our telescope view down here that we seem to have just a perfect view there of Cygnus the Swan. Okay, we should have what we need now. I'm going to go down to a 20-second shot at 2000. I'm going to try that and see what we get. 20 at 2. I'm going to show you the colors of Albireo first. Okay. Oh, look at that. Isn't that beautiful? Now, it's a little more blue hued because of the filter. Okay, but look at how beautiful that looks. Wow. And here's another thing too. Let's bring up some of the data on Albireo for a second. The distance of Albireo is 385 light years roughly, and you know this program doesn't get it exactly right. All right, 385 light years. This distance between the two components that make up this double star is over 5,000 astronomical units. Now, just to give you an idea, that's literally 12 to 15 times the distance from the Sun to Neptune. Okay, so we're talking about a massive distance between these two stars. And I think somebody another night asked me, what would happen, if Jupiter suddenly became a star? Well, that would spell disaster for our planet for sure, because, and of course, it could never become a star. It's not big enough. But another star in the night sky would be disastrous because it would be bathing us with radiation. Now, here, at 5,000 astronomical units, it's somewhat possible that, depending on the star, that planets around, say, one of these stars, let's say this. See, this is a B8, so it's almost an A star. So we might be able to get planets around this star, but they would have to be far away to be in habitable zone. Not 5,000 astronomical units, but far enough away so that the radiation from this star and the radiation from this other star might be enough to spell disaster for any life there. But it's just a beautiful double star. I think some of you out there, you should write a little short story about Albireo, a science fiction story, and talk about how Albireo is the home of a race of beings, the Albirians, or something. That'd be kind of cool. Just floating an idea. Okay, now let's see. While we're here, I will bring us down to check out the dumbbell tonight, because the quality of the dumbbell will tell me more about the quality of objects in this area of the sky.
Mark, K2Q asked how much larger than our sun are these stars. You could probably quantify it better than I could.
Well, the K2, the orange star, is a star that is a type luminosity class, rather, of the Roman numeral 2, and that puts it in the giant range, or supergiant range. So it's going to be much bigger than our sun. Its actual diameter I'd have to look it up for you, Katie, to be honest. But it's going to be somewhere in the neighborhood of maybe out to the orbit of Venus, maybe a little more, maybe a little less, not quite sure. But the B8 star is actually not a supergiant at all. It's actually just a regular star like the sun, but it's going to be a little more massive, and it's going to be more hot and blue. But it's called the luminosity class 5, which is what our sun is, and which our normal stars are. So I hope that helps. I'm not sure. I'm just going to do a quick finder shot here. I think it should be right in the middle here. Right there. That's my guess. I can't really see it here because it's bright enough to see, but I think it's going to be right where my cursor is. But it might be flipped. I might have to rotate the image. Yeah. Okay, I have to rotate the image. Yeah, and then it's right where my cursor is. Okay. All right, well, 20-second shot shows it right there. Now, this is kind of how it looks to your eye, which is why I took that photo for that amount of time. In a modest telescope, this is what it looks like to your eye when you look through the eyepiece. Right? However, in an immodest telescope, a telescope that actually has a lot more going for it, we could actually go, let's say, to 8,000 here and do the same 20-second exposure. We went up several stops.
Katie, they appear to be so close together because they're so far away. And when he says 5,000 astronomical units apart, that's 5,000 times the distance between the Earth and the Sun.
Yeah, or about, 10 to 15 times the distance, 12 to 15 times the distance from the Sun to Neptune.
You see the dumbbell right there? That's a good example of why I think of it as the apple core nebula. Like somebody ate an apple.
Yeah. And that blue little star right there, that is a white dwarf, once again. So you look at this and you say, wow, this is just an incredible sight. We took a lot of pictures. I think I'm getting a little either cloud or dome interference here. And I actually, to be honest, I wasn't actually thinking of streaming tonight. And it looks like we've got some light clouds actually. So normally you've seen how these look. We see this beautiful dark sky. But I can see that we have some light clouds here in our all sky. This is the Arizona all sky cam that I'm using here. It'll be in Arizona before long too. And it's probably going to go out sooner than later. It might go out right away in July along with the computer, and then I can set it up on the computer. And if I can set up and get the pier done as well, because the pier, I have the pieces here for the pier. I'm going to ship them out to Arizona, and the pier is going to be welded out there, because why ship a 150 200 pound pier out to Arizona when you can just make it out of smaller parts. So I had the parts laser cut up here out of stainless or out of steel, and out there it's going to be welded together to form a pier, and then that pier will be bolted down to the concrete pad after cutting a hole in the floor of the shed, that is to say the observatory. And we got to run power conduits as well as network conduits. We're not doing anything with Wi-Fi or Bluetooth, just so you know, because Wi-Fi and Bluetooth are problematic at best, and I don't want any points of failure, so we're going to be hardwiring everything. We're going to have hardwired Cat5 cable running 150 feet back to a router, and then we're going to hardwire the power, of course, and we're going to hardwire straight to the output from the solar panels and then the batteries. And so we'll be able to, again, it's a green observatory. It's going to be totally off the grid and using all renewable energy. Oh, see that? looked in the live view and we saw a satellite go right through. So 12:25 and about 18 or so, a satellite went right through. So yeah, we're going to be using full all green power. I love it. Yeah, it's the way to go. I didn't even think I was going to stream tonight, by the way. I was going to just do some shots of the Ring Nebula. And then I thought, well, maybe some folks would like to see this, and just hang out here and have a place to go and hang out. And I thought, well, that's nice. I'll do it. Why not? So welcome to you guys. If I haven't said so already, I want you to know that you guys mean an awful lot to me. I don't have a need for all kinds of attention, but I do have a burning desire to see people learn about science, because that's what's missing in our schools. Our curriculum in schools just doesn't have doesn't have science at the forefront, and that really bothers me. This would be the same kind of picture but with less grain. So that's what this is about. That's why SkyTour LiveStream West, that's why SkyTour LiveStream East. And we're going to use identical telescopes here and there. So we'll be taking, for instance, pictures of the moon from here, pictures of the moon from there, and then making 3D images of the moon that have never ever been done in human history before. I think that's a cool idea. Now, if someone goes ahead and does it, well, that's just they're trying to spite us to get it done first. Okay, fine, that kind of thing. But I don't lose sleep over that stuff. Science is for everybody. Yeah, this is actually, okay, just a little bit wonky. It walked a little bit. And I think we're looking through some high clouds. That's what this reddish thing is here. Normally, if it's the dome, it's going to not just have a tiny little interference thing. It's going to have a global thing throughout the whole image. So we are looking at through some light clouds. But hey, it doesn't look bad for light clouds. Okay, let's see here. I skipped right by Measure 56. So I'm going to run back to it. What do you say?
Sure, why not?
Yeah.
I can't see your chart very well. Is that a globular?
Yeah. And we're going to go to Albireo as the finder star, which is going to be right here. Albireo will just be right there. It'll serve as just a little a star that's going to be used for basically a hopping point, and then it's going to disappear, and when it does, we're going to go zip right over to Measure 56, and away we go right now. And you can see the telescope is heading over to here. Okay, Measure 56 is now in the house. Can I see it? Well, no, I can't, but when I take a picture, I will. We'll do 20 seconds at 5,000. We have to wait about 11 seconds for the acquisition period of the guide star to occur. And then we can take our photo. Hey there, Troy Llewellyn. How are you? Well, I'm glad that you like it, Troy. I'm very happy to do this. I mean, I hope it's not too infectious. I know I've actually several people that were watching our stream have bought telescopes just directly because of watching the stream, and I've helped them to set them up. I wanted to make sure that they were comfortable with it, because that throws people off, makes people feel terrible. They invest all this money and time only to find out that they feel like they're idiots because they can't set up the telescope. Well, that is just baloney. You know, it's just that the instructions were not written in a way that make it accessible to you. I've faced that a million times. I know what that's like. This is M56. Look at that globular, huh? Now, what's interesting about this globular is we're looking at this globular into the disk of the galaxy. I mean, this is right where the plane of the galaxy is. If we look quickly at our map, you'll see M56 is right here, and here is the galactic plane, okay? So what that tells me and you is that this globular cluster, right, which actually, let's get the globular cluster, here it is. This globular cluster is just about 32,000 light years away. So that means that it's about the same distance to this globular cluster as it is from here to the center of the galaxy. And for us, that center of the galaxy is down here in Sagittarius, okay? In this direction. And we're about 33,000 light years from there. And we're about 33,000 light years from this globular cluster. So it's not outside the galaxy. It's actually racing through the disk of the galaxy, either one way or the other. And when these clusters do this, and this is sort of like my thought process. When they do this, I'm feeling very strongly that these are probably either, when they race through the galactic disk like this, they're going to lose stars and shed stars behind as they get gravitationally caught by other stars or other clusters, or they themselves might pick up some stars as they race through. So if we ever see odd stars in a globular cluster, I think we have to consider that maybe they were picked up along the way, because these are halo objects. They orbit the entire galaxy as a whole, and they go plunging through the galactic disk in some cases. You know, so maybe that is something that would make sense. I don't know. It just seems like common sense to me. What do I know, you know? But so this has been a fun night. I got my photos of the Ring Nebula, which I will foist off on you with all the others after I stack them. And then I got a few extra photos here, singular objects to show you. So we got this beautiful globular cluster right there. We took a few pictures of the Dumbbell Nebula, okay? And we could see that the Dumbbell also has this beautiful, little white dwarf in the middle there, which is really kind of cool. And then we actually took some photos. This is also the Dumbbell's an earlier shot. And then I got some photos, let's see, of the ring. We did the ring, and we did a lot of the ring because I wanted to show, I wanted to get a lot of the ring done, because my intention is to really stack a beautiful. Get on me, watch it! Almost hit me! Get away! Was to stack a nice shot for you. So, and I think it's really pretty. Looks really nice. All right, so that said, my research for tonight is done, and so I want to thank you guys for coming out. I didn't see any questions, so I saw some, obviously, but I will be available for questions anytime you want. You can just find me at SkyTour Radio at kgraradio.com, and I'll be happy to answer your questions if you have any. So that's the other thing too, is I'm always available. I'm not gonna, I don't hide behind, anything. Let's see, SkyTour Radio at kgraradio.com. Okay, that's the email. If you want to send me an email, you can send it to SkyTour Radio. And don't forget SkyTour Radio, Sunday nights, 8 to 10 p.m. Eastern Time. And while you're at it, don't forget Friday nights at 7 p.m. We have, I see you're smiling already, we see We have Behind the Obsidian Curtain with Carol Carl, who is in the chat. You know, she's so humble. She doesn't announce, I'm Carol Carl with KGRA's radio show. But Carol is an amazing lady, and I think that you should listen to Behind the Obsidian Curtain. She has the most incredible guests on her show. SkyTour Radio isn't really a guest type show. It's more of we're learning astronomy together. So I have Daryl with us, we have Amanda with us, and we'll talk about astronomy. And Daryl will bring us some excellent stories and about the night sky for what to look forward to in the upcoming season, and an amazing amount of he has an amazing amount of knowledge, you know. So it's two different approaches to astronomy, you know, and Daryl's approach to astronomy is really a fascinating one because you know, he came from the point of view of building instruments and looking through and seeing with your eye, and I'm going from a point of view of, well, yeah, I love the instruments and love looking with my eye, but I want to record, I want to see an image, I want to record images and make the images spectacular. So I think that you know, together, I think Daryl's knowledge and mine complement each other on SkyTour Radio in that regard. And you know, I mean, when you're an astronomer, you just never ever, you know, wake up early in the morning. But I have to actually shut down tonight because I do have early morning pickup coming here. I've got Navy guys coming up to pick up a model. Sorry, I got a Navy model that has to go out. And I have to be up ready to send that out around 8 a.m. So I do have to go to bed. Trish D, how are you? And I just, I don't want to shut down, but I've got to. I mean, when I opened up, I knew I was going to have trouble shutting down. I always do. Anyway, folks, I thank you for being here. You're wonderful. You make the difference for me. I'm sure Daryl feels the same. Amanda would too. She couldn't be here tonight. Actually, I sent her a message, but it was so quick that I didn't hear back in time. And you know, she probably will feel bad she couldn't join. You know, she always does. And I told her, hey, no worries. I know it was quick. I don't expect miracles. So anyway, you guys have a good night. And I'm going to have you guys a Ring Nebula to remember when I get back, okay, from getting all these images off the Observatory machine. And that'll happen this week. Okay?
Good night, everybody.
All right, folks. You guys have a good night, and we will talk to you soon. See you later.